Let's do an example related to the previous theorem. Here is an example for A 2 1 3 5 3 and with A inverse. A and A inverse are given -5 and 2. So this is A and this is the inverse of A. Both are given. Verify that A inverse A is identity. Here is the solution. You have to just multiply A and A inverse. Here is A inverse 3 minus 1 minus 5 2, and here is A. If we multiply both, we get 6 minus 5 3 minus 3 minus 10 plus 10 minus 5 plus 6, which is identity matrix. Hence it is I2, and yeah, this is proved because both are inverses and we have to prove this. This is equal to I2. Look at another theorem. If this is the theorem. If A and B are invertible matrices, then of the same size, then AB whole inverse is equal to B inverse A inverse, and you can see that this is not equal to A inverse B inverse. This is wrong and this is true, because whenever you will take the inverse of the product and you want to distribute the inverse on both, then you have to change their order. This is the main task of this theorem. Here is the proof. Since the inverse of AB is equal to this, which means if we multiply this AB with this element, it must gives us identity. So here is the proof. What does that mean? If I multiply the inside AB without inverse with this thing, B inverse A inverse, I should get identity. If I am getting identity, so that means these both elements are inverses of each other. So if they are inverses of each other, that means this is true, and this is what we have to prove. So just multiply A. First we use the associative property of matrices with respect to multiplication. What is associative property? Associative property of matrices with respect to multiplication says, if you multiply these two first or these two first and then the whole thing with each other, or if you multiply these two first and then multiply the rest with this, you will get the same result. So in other words, if I change these brackets here in this way, so the result will be unchanged. What does that mean? B times B inverse, here are the brackets. This is called the associative property. That means if we change the brackets from these two to this, it will cause no change. Since B and B inverse are inverses of each other, so if I multiply B and B inverse, I will get identity. So this is identity, okay, times A inverse. So if we multiply identity with any matrix, we will get the same matrix. Okay, if I multiply identity with A inverse, I will get A inverse. Again, A and A inverses are inverses of each other, so they will give me identity. So you can check, I multiplied the matrix inside the inverse with this, I got the identity. What does that mean? This means the inside matrix and this matrix are inverses of each other. Okay, so I can write the inside matrix A and this matrix are inverses of each other. In other words, the inverse of this is this, the inverse of this is this, hence it is proved. This is what we wanted to prove. So now look at an example. We have two matrices A and B, and we are asked to verify this property, the property we have just proved as a theorem. So to prove that this is equal to this, we need to compute both sides of the equations independently, and then we will compare that they are giving us the same result or not. So let's compute the first side, the left hand side of this equation, and then we will compute the right hand side. So let's compute the left hand side first. In the left hand side, you have this A, then this B, and the inverse. Okay, so I will multiply first the matrices inside these two. Look at the multiplication. This is the multiplication of the matrices inside. So I have multiplied these two matrices and did nothing with the inverse. Okay, so now I will simplify. I get this thing, this matrix, but I will do nothing with the inverse. So until now we have just multiplied the matrices inside. Now our aim is to take the inverse of this matrix. How to take the inverse of the matrix? We have the formula. Okay, to find the inverse of this matrix, we have to consider an augmented matrix here. I have wrote this matrix and the identity matrix. So my aim is to make here 1 and then to make here 1. How can I make this one? If I divide R1, row 1 by 3. And how can I make this one? If I divide R2 by 3. So I will do these two operations. I have divided R1 by 3 here, and then I have divided R2 by 4 here. I got this matrix. So now my aim is to make this 0. How can I make this 0? If I write 8 by 3 minus 8 by 3 times this one. Okay, so the first 8 by 3 is R1 and the last one is R2. So what is meant by this? This means R1 minus 8 by 3 R2. So this operation I will perform, this one. So if I perform this operation, I will get this. You can check R1 minus 8 by 3. So R1 is 1, 8 by 3, 1 by 3, 0. 1, 8 by 3, 1 by 3, 0. This is R1. You can check. And then minus 8 by 3, minus 8 by 3 everywhere. You can check. It's everywhere. And then R2 is 0, 1, 0, 1 by 4. 0, 1, 0 and 1 by 4. So everything I have written as to solve. Okay, now my aim is to simplify this. So after simplification, I got this result, and here you can check that here you have an identity matrix and here you have something else, and this something is the inverse of the matrix which we had considered at the start. So the inverse of this matrix is this matrix. Okay, so the result of the left hand side is actually 1 by 3 minus 2 by 3, 0, 1 by 4. This is the left hand side. Now we will consider the right hand side. In order to find the right hand side, we have this thing which is B inverse, A inverse. So we need the inverse of B and then the inverse of A independently. Now we will compute the right hand side of that equation. In order to compute the right hand side, you can see that we need A inverse and B inverse, because right hand side was B inverse, A inverse. So we need the inverses of both A and B. So first of all, we will compute the inverse of B. So in order to consider the inverse of B, we need the augmented matrix B with the identity. You can see this is B and this is identity. So we have computed the augmented matrix. Now we will perform the row operation. My aim is to make this one. How can I make this one? I can divide R1 by 3 to make it 1. And similarly, then I will make this one. So that means I can divide R2 by 4. So I will perform these two operations, divide R1 by 3 and divide R2 by 4, and then you will get 1 and hence here 1. So this thing becomes identity, and this is the inverse of B. So hence inverse of B is this. Now we will compute the inverse of A. In order to compute the inverse of A, again we need the augmented matrix of A with the identity. Here is the augmented matrix of A with the identity. Now my aim is to make this 1, but this is already 1. And my aim is to make this 0. This is already 0. Now I will make this 1. So this is already 1. Only change will be done by me is that making this 0. How can I make this 0? I can make this 0 by 2 minus 2 times 1. That means R1 minus 2 times R2. If I make this these changes in R1, then this I will get these calculations. So after simplification of these calculations, I will get this result. In this result, you can check that this is the identity matrix and this is something else. So this thing is the inverse of A. So I can write the inverse of A is equal to this thing. So I have got both inverse of A as well as the inverse of B. Now I can compute the right hand side of the theorem. Hence the right hand side is B inverse A inverse If I put the values of B inverse and A inverse, which I have computed, and then if I multiply, and after simplification I will get the answer for the right hand side. And if you see, this is the right hand side. Remember, now I will check what was our answer of the left hand side, whether it was the same answer or it was different. So remember, this is 1 by 3 minus 2 by 3, 0, 1 by 4. And where is the left hand side? Left hand side is this, 1 by 3 minus 2 by 3, 0, 1 by 4. So both are same. So there is no change in the left hand side and the right hand side. Since both are same, so I can write left hand side is equal to the right hand side, hence proved.